Hello, and welcome back to the channel, where we explore everything and beyond. Today, we're going to talk about the client-side data model, and more importantly, how that data model makes dynamic views possible. In the previous videos, we established something important. The UI cannot be hard-coded. The client doesn't know ahead of time what views exist on the server. It doesn't know what fields they have. It doesn't know how they relate to each other. Everything comes from the server. That same principle applies to the data model. If the UI must be dynamic, then the data layer must be just as dynamic. Since we're communicating using JSON RPC, the views arrive in XML format and the model definitions arrive in JSON format. The client reads those definitions and builds its internal representation at runtime. Let's take a look at the simplified class diagram. And just to be clear, the client-side diagram shown here is for this experimental client, not the official web client. On the server side, you'll see classes that deal with storage and backend logic. On the client side, although we share similar concepts, the purpose shifts. Now, at first glance, the client-side classes may look like a port of the Python code from the server. You'll see classes like model and field, and the naming feels familiar. But this is not a one-to-one mirror. The responsibilities are different. On the server side, Tryton handles persistence, business logic, validation, indexing, and performance optimizations. For example, a server-side model might define database indexes to improve query speed. Those indexes are never sent to the client because the client doesn't need them. The client has a completely different focus. Its job is not to store data permanently. Its job is not to enforce all business rules. Its job is not to optimize database queries. Its job is to bridge server-defined structure with user interaction. Now, let's zoom in on the client side only. When you look at the structure, you'll see four main pieces: model, field, record, and record set. To really understand this design, it helps to think of it as layers of responsibility. First, the model. The model does not store actual data values. It doesn't know what the current record contains. Instead, it describes the structure of a model. When the client loads a model definition from the server, the model class loads the field definitions. It creates field instances based on their type, and it allows other parts of the system to ask questions like, what field exists? Or what type is this field? It defines the shape of the data. Next, the field classes. Each field represents a specific type of data, and their most important responsibility is conversion. When data comes from the server, it might not be in the format the client wants to use internally. So the field handles that transformation using methods like toInternal. And when the client needs to send data back, the field converts it back into server format using toServer. This keeps the rest of the client clean. The UI doesn't need to know how the server encodes values. It just works with the internal representation. So, at this point, the model defines structure. The field defines behavior for each type. Still, we haven't stored any actual record data. That brings us to the record. This is where the real data lives. And this is very important. Views do not render data from the model. They render data from record instances. If the model is the blueprint, the record is the actual object built from that blueprint. A record holds the in-memory state of a single entity. It tracks values, modifications, and states. It provides methods like load, save, cancel, and rollback. But here's something critical. The record does not synchronize directly with the server. There is a separate communication layer responsible for JSON RPC calls and server interaction. Previously, we've already discussed the login flow, which uses the communication layer. We will discuss more on that layer in a future video. The record focuses purely on managing client-side state. That separation keeps the architecture clean and easier to reason about. Then we have the record set. If a record represents a single entity, a record set represents a collection of them. Tree views rely on it. Relational fields like many-to-one and many-to-many rely on it. Whenever multiple records need to be managed together, the record set steps in. Just like record, it handles in-memory state only. It provides methods such as load, add, remove, and unremove. No persistence. No direct communication. Now, at this point, everything might seem straightforward. But here's where things become more interesting. This entire structure is recursive. A record can contain relational fields. Those relational fields reference other models. Those models define their own fields, some of which may also be relational. So the structure can expand indefinitely. If you've been following this series, you may recognize this pattern. It's similar to how views are nested. It's similar to how menus contain submenus. In a fully dynamic client, recursion is not just a design choice. It's a necessity. The client must be able to interpret and construct structures it has never seen before, and those structures may contain other structures. That's the foundation of a truly generic client. With these classes in place, the next step is connecting them to the views. To do that, I introduced several composables. These composables act as a bridge between the views and the data model. For example, when the user clicks on a side menu, TreePage view is rendered using the useTModelView composable. And when the user double-clicks a row in the tree view, FormPage view is rendered using the same composable. To render the actual prime view data table component, components like TreeViewView, one-to-many field, view, and many-to-many field, view use the useTRecordSet composable. And for individual fields, the field widget component uses the useTField composable. These composables tie everything together. View definition, model structure, record state, field behavior, all working dynamically. So if we zoom out and look at the big picture, the server defines the structure. The client builds a dynamic representation of that structure. Records hold state. Record sets manage collections. Fields handle type behavior and conversion. And a separate layer handles communication. Together, they allow the client to render and manage any model the server sends, without knowing it in advance. And that's what makes this architecture powerful. That's it for today. If you'd like to follow the progress of this project, consider subscribing to the channel. Feel free to like and share this video with anyone who might find it useful. Thank you for watching.